All right, all right, all right. So today we're doing problem 888, fair candy swap. And besides the beautiful numerology of 888, I found this problem to be appropriate because, well, it requires sufficient reasoning, which I believe translates well to the daily role and requirements of being a software engineer. But also, it's not so heavily dependent on data structures and algorithms that it requires somebody to have a strong foundation in that, which is often only semi-relevant to your day-to-day work, right? It doesn't require a strong foundation in that in order to be successful in solving this. So this is a perfect problem to give someone who's, a junior engineer or, entry level, intern, because it really establishes your capacity to reason through a problem and not so much, the data structure and algorithm stuff, which is fun, but not always super relevant. So with that said, let's go ahead and get right into it. Okay, so Alice and Bob have a different total number of candies. Okay, so there's a person Alice, there's a person Bob. All right, let's do a little diagram, right? I didn't bring my tablet out here for nothing. All right, so we got, we'll draw Alice in purple, I guess. So we got Alice over here. All right. And we have Bob. All right. Bob and Alice chilling out. Okay. And you're given two integer arrays, Alice sizes and Bob sizes, where Alice sizes is the number of candies in the ith box of candy that Alice has, and Bob sizes the number of candies of the jth box of candy that Bob has. What does this mean? Super wordy. Basically, each person has an array, slices, that corresponds to the candy that they have, right? So each index of the array is the box, and then the value is the number of candies that's in that box, right? So, for example, we'll use the example here. We got 1, 1, and 2, 2. Okay, so Alice has two boxes of candy, one with one candy in it, and another one with one candy in it. And corresponding, Bob has two boxes of candy as well, one with two candies in it and another one with two candies in it. Okay? And since they are friends, they would like to exchange one candy box each so that after they exchange, they have the same total amount of candy. Okay, so that makes sense, right? If I have boxes of candy, I could remove some candy, remove a box, give it to you. Now I've lost a bunch of candy. You just gained a bunch of candy, and you could remove one of your boxes and give it to me. So you'll lose a bunch of candy, and I'll gain a bunch of candy from that, right? So we can do a little exchange, okay? The total amount of candy a person has is the sum of number of candies in each box that they have. Okay, so if you look at all the boxes, add up all the candy, that's the total candy you have, right? So Alice, for example, has two candies, right? She has two boxes with one each. Bob has four candies, right? Because he has two boxes with two each, right? So that makes enough sense. So we're going to return an integer array answer where answer 0 is the number of candies in the box that Alice must exchange, and answer 1 is the number of candies in the box that Bob must exchange. If there are multiple answers, you can return any one of them. It is guaranteed that at least one answer exists. Okay, so this problem is pretty intuitive in terms of like, okay, this makes sense, right? Like, okay, we're going to do some exchange. How much are we going to exchange? How are we going to figure that out? Well, that's really where the reasoning needs to play a role, right? But, Alice has two candies. Bob has four candies. All right. So there's going to have to be some transfer here where she gains a candy and he loses a candy, right? Because he's got too much and she's got too little. So he's going to have to give her more than she gives him. And how's that going to work? Well, it turns out that the answer here, right, is if Alice gives her one box away, right, and Bob gives one of his two boxes away. Now, it's kind of arbitrary here because they only have twos and only have ones to give. Well, what happens? This results in Alice having the new box from her friend, Bob. So we'll do it like this. So she still has this one here, and he still has this 2 here. But now he's given that 2 to Alice, right? He's given Alice that 2, and he's received that 1 from Alice, right? So now Bob has 3 units and Alice has 3 units, right? So there was an exchange that occurred and now they both have the same. So our answer is this 1, 2, right? This corresponds to what Alice had to give and what Bob had to give to make this work, right? Now, you can go down, even though this problem is simple, it's easy to go down weird rabbit holes to try to figure out how to do this, right? Even though it's pretty simple. And one thing I would always say in these kind of problems is if you have a mathematical kind of background, right? If you've taken algebra, if you've taken calculus, if you've taken a lot of math classes where you're used to using these kind of reasoning mechanisms with variables to try to get through a problem, lean on that, right? Because you could look at this and be like, well, the difference is, you know, I'm about to do some incorrect logic here to try to get you. It's like, well, we need the difference to be 2, right? Because, well, he has 2 more. But, like, the sum of this is 3. Right? So that's not 2. So how would you get 2? So you can play weird games to try to get this to work. But it's better to just kind of reason through the problem in terms of, like, what's going to happen? What do you have? What do you not have? And then resolve to an answer. Okay, now, how does that work? Okay, so what we're going to do here is we're going to call this value B. Okay, and we're going to call this value A. All right, so A is the sum of candies that Alice has. Okay, so let's do a little mathematical stuff here. So let's say that A equals the sum of Alice's candies. Okay, and let's say that big B is the sum of Bob's candies. The candies of Bob. Candies of Bob. Okay? So that's just because we want to make, like, we're trying to make this sum the same at the end, right? So we want to make our new sum of Alice's candy, we'll call that A star, equal to the new sum of Bob's candy, and we'll call that B star. Right? So that's what we want it to be at the end, right? Because they have their sums initially, so it makes sense that we're taking the sum because we need to figure out what the sums are to determine out what do we need to exchange in order to make this work, right? And if you read the answer, right, there's always an answer, so it's always going to work for something, right? What is Alice's number of candy at the end? Okay? At the end, Alice's candy is going to be what she had initially, right? So let's just walk through this problem. Alice initially has A candy, right? That's this value here. And then what happens? Well, she's going to lose a package of candy, right? Because she's going to have to give that candy away to Bob, right? So whatever her initial value, she's going to lose some candy because she has to give one of her boxes away, right? And that corresponds to our answer, right? Our answer is what Alice ends up giving and what Bob ends up giving, right? So let's keep this consistent here. Right, so Alice is going to lose A candies in this answer, right? This is the answer here. Like, for example, here, right, Alice gave 1. So the A value here, right, if we wanted to map all these, that's A, that's B, right? That's what Alice ends up giving. That's what Bob ends up giving. So Alice started with 2. She lost 1 when she gave it away, which made her answer 1, and then she gained 2 to make her answer 3, right? And then same with Bob. Bob started with 4, that's the B value. He lost 2 to make it 2. He received 1 to make it 3, so that's why these sums are the same, right? So Alice's amount of candy in the end is, well, she has A candy initially. She's going to lose little A candy, right? That's what she's going to end up giving Bob. And then she's going to gain B candy, right? What about Bob? Bob, very similar, right? Bob, in the end, this B dash thing, he's going to, let's make this all consistent here. Bob's going to have his initial amount of candy, but he's going to lose the candy that he gives Alice, right? He started with some amount of candy. He gives one of those packages away. That's no longer his candy anymore. He's going to lose some candy, and he's going to gain whatever Alice gives him. Okay, so we have a lot of variables here. It looks pretty complicated, but we're going to simplify this and think about how we're going to solve this in a moment. All right, but remember, these things need to be equal in the end, right? what Alice has at the end and what Bob needs to have in the end, those things need to be equal in the end. So we need to set these two things equal to each other. The only things we know right now, right? We're trying to find A and B, right? So that's a little complicated, right? We're trying to find A and B. We know what A and we know what big B are, right? But we need to find A, little a, and little b. That's literally the answer. But we know what these are, and then we'll walk through how we can kind of manipulate this and programmatically make this work. Right, but these things that need to be set equal to each other. So we have A, B. So we have A minus A plus B equaling, and then on the other side we have B. Sorry, I'm trying to get cute with this, and it's not a good idea. Let me move this over so you can see that. B, and A. So this is A minus A, B plus B minus B. All right, so that's our formula here, right? We know, like, things we already know, right, is we already know what B is. Right, we already know B. We already know A. Right, but these are the B and A value that we're trying to find. So you might look at this and be like, dude, so like, you got me here, right? We got here, but now what? Like, yeah, we need to find B and A. I know it means a little bit better now because we have a formula. We can think of it in terms of other things, right? Which is good. But it's like, how are you going to make this work, right? Because there's still two things that are unknown. Okay? So what you can do to resolve these unknowns is you can try each A value, right? Because basically each A value, if it's going to make this work, there's going to be a corresponding B value that makes it work, right? So we can plug in, right, like for Alice in the initial problem, right, she had 1 and 1, right? She had 1 and 1. So what we could do is we could plug in the A's. We already know what the big A's and the big B's are, so all we'd have to do is solve for B, right? We know that Alice has 2 initially. We know that Bob has 4 initially. And if I use one of the A's that Alice has, right, which is 1 right over here, right? Alice has 1 and 1. So if I use one of the A's that Alice has as 1, I could subtract that out and say minus 1 plus B equals 4 minus B plus 1. All right, and then I could solve for B. And if you solve for B here, let's do some quick math. We get B plus B, that's 2B. That's 5, 6, 4. 2B equals 4. 2B equals 4. B equals 4 divided by 2. B equals 2, which is our B equals 2 value, right? So, but of course, you don't want to leave it in this form, right? So what I'm basically saying here is, right, you have this formula, but the problem is that you have 2 variables. So in order to eliminate a variable, what can you do? You can just start trying each value within Alice, right? Look at each value and say, does this value work? No. Does this value work? No. Does this value work? No. And how would you know if the value works? If the corresponding A value if the corresponding B value is in Bob's list, then you know that, okay, Bob has a value that would make this work, right? Like, basically what you're doing in this problem is you're saying Alice and Bob are trying to figure out which packages to switch, right? To swap, the boxes to swap candy. So Alice says, here's a box, right? Do you have a box that you could give me that would make it even, that would make our sum the same if I gave you this box? Right? That's basically what Alice and Bob are doing. Alice and Bob are talking. Alice is saying, what box are we going to swap? And Bob says, I don't know. And Alice says, what if I gave you this box? He'd say, okay, if you give me that box, he'd look at this formula and say, all right, then I'd give you this box and it would make it even. Or Alice gives him a box and Bob says, sorry, there's nothing I can do, right? You're giving me a box I don't have any corresponding box that I can give you to make this average, right? Like if Alice had 1, 1, and 2, and Bob had, I don't know, I don't want to do this on the fly, so I'm not going to do it. But hopefully that makes sense, right? The idea is that Alice is going to keep giving him boxes, and he's going to follow this formula to determine if he has a corresponding box that he can give her to make this situation work out, okay? So in order to do that, what is the formula? We don't want to leave it in this form, but if what Bob's going to do is he's going to say, well, I'll know what Alice gives me. So when Alice gives me an A, I know what Alice has, I know what I have, and I know what Alice just gave me, so what do I need to give her? So that's solving for B here. So we have, I'm going to leave it in normal form here. So 2b equals b, or not to, no, 2b equals b plus a minus a plus a. All right, so then we have 2b equals 2. I already messed up here, guys. Isn't that crazy? Let me just do this really quick. Okay, so apparently I can't do algebra anymore. So we have 2b equals b plus little a minus big A plus a. So I'm just moving things over, right? So then we have 2b equals b minus a plus 2a. So then b equals 1/2 times b minus a plus 2a. Sometimes algebra can be hard, especially when it's been years since you've done. Well, I guess I do that kind of stuff in these problems all the time, but it is definitely a challenge. Yeah, so we have apparently what Bob has to give Alice when Alice gives him A is 1/2 times what Bob has, minus what Alice has, plus 2 times whatever Alice just gave him. Right? Maybe you can reason through why this is the formula, but it's harder to derive this just by looking at this and trying to reason like, all right, if he gives me 1 and you give me 2, maybe you're smart enough to do that. I'm not. For me, it's easier to leverage formulas to say what's going to happen in the end, set them equal, and then determine what it is that Bob has to give Alice. Okay, so how this is going to work essentially is Alice is going to give, let's look at this example. 1, 2, 2, 3. All these examples stink. Ugh. No. So what Alice is basically going to do, Alice is going to give an A to Bob. Bob's going to put this A through this formula at the top and ask, do I have he's going to ask, do I have the corresponding B? And if he does, he'll return that back to Alice, and then they have convergence, right? So Alice is basically going to say, here's an A, Bob. Bob's going to take this A and put it in this function, and he's going to say, okay, I get this B value. Do I have this B value within my packages, right? Do I have the corresponding box of chocolate? And then he's going to say, okay, Alice, I do or I don't. And if he does, then the problem's done, right? So Alice looks at each A. Alice gives an A to B to Bob. Bob figures out if he has the corresponding B in his list. If he doesn't, they do it again. If he doesn't, they do it again. Then Alice tries another A. They try it, doesn't work. Alice tries another A. Bob puts it in the function, gets B, figures out that B's in his list. They're good, and then the problem's done. Okay, so let's go ahead and just write the code for that. All right, so we need to know what A and B are. So A is the sum of Alice sizes. B is the sum of Bob sizes. All right. And then we just walk through this formula, right? So we look at for each A and A that Alice can give. Now this is where Bob's going to ask the question, right? Bob's going to ask the question. Bob's going to ask this question right here. Do I have this B value? B equals 1/2 B minus A plus 2A. All right. B equals 1/2 times B minus A plus 2A. B minus A plus 2 times A. And then he's going to ask the question, well, if this B value is in the candies that I can give, right, then we just found a match. So we return what Alice just gave, which was A, and the B value that Bob gave. All right. Now, a couple things here first, right? A couple coding specific discrepancies we have to think about, and then we'll optimize this. All right, the first thing is well, this is going to be a floating point number, right? Because what if 2a, b minus a plus 2a is odd? There might be a proof that I can never, I don't know. But, you know, if that value is odd, then what? If that value is odd, well, now we're going to be in big trouble, right? Because then when this gets divided, it's first going to be a floating point. So you could try first saying, oh, I'll just divide this by, I'll floor divide this by 2, right? But then, well, the issue there is if you floor divide, right, you might not actually get a value that makes sense, right? When you do this division, given the value that Alice just gave Bob, you might get like 3.5 packages of candy, right? I mean, 3.5 candies. I need a box with 3.5 candies. Well, that doesn't exist, right? The boxes only have whole number of candies. So when you floor divide, it'll floor divide it down to 3. And then Bob might actually have a box with 3 candies, right? So then he thinks, oh, I'll just give her the box with 3 candies because that's what this formula said. But it doesn't actually sum up correctly, right? Because you actually, given the candy that Alice just gave you, you actually need like 0.5 boxes of candy, right? So basically what I'm saying is that this floor divide can mess things up. So what you need to do first is ensure that you can floor divide, right? So instead of saying B in B cases, just to make this simpler, right, we'll say that's what our B value is. But also, this will only work if B is even, right? If it can be divisible by this system. All right. So basically what I'm saying is like, you can't just floor divide it by 2 because it's going to remove the component where your system isn't divisible, right? So you're trying to ask for something that doesn't result in a whole number of version of candy. So if you floor divide, it's going to remove that component of the floating point. And then Bob's going to think he can give a candy that's not actually a full number. Hopefully that makes a little bit of sense. Okay. Int object is not iterable. Oh, because I'm going to look at all of Alice's candy. She's going to try each of her candies. And then Bob's going to say, can I get that corresponding V value in Bob's sizes? It's always okay to make mistakes like this. Not a big deal. You're just trying to run through. B is not defined. Oh, shoot. Because maybe it would have been better to do it the other way. But all right. Now, maybe this won't pass. I don't know. So we have the right answer, right? And 18%. That's actually faster than I expected. So we passed the solution, right? But if we want to improve our runtime, there's a little tweak we can do, right? Which is, let's just look at our runtime first. Okay, so let's say that n is the length. All right, n is the length of Alice sizes, and m is the length of Bob sizes. All right, so we sum this, that's going to take n time, right? We sum this, is going to take m time. So we already have big O of n plus m doing that. All right, now where it gets hard is for each of Alice's elements, Bob has to look through his whole list to see if he has the corresponding box with the correct number of candy, right? Because every time Alice says, what if I trade you this one? Bob's gonna be like, okay, well then that means I would have to trade you, B many. So then I need to look through the whole list and find if I have that B many, right? So for each of Alice's candy, Bob could potentially have to look through the whole list to find if he has the corresponding candy to give her. So that means that it's gonna take, for all n candies that Alice has, Bob has to look through all m elements. So that's n times m. So that's plus n times m for our time complexity. Okay, now for space complexity, the solution is actually better. Now, of course, this O of n and m term, they get, overshadowed by m times n, but I'm going to leave it there for a moment because we're going to prove this. All right. So our space is actually constant because, well, we don't have to create any variables, right? We literally just leave Bob sizes, Alice sizes, we sum them into 2 variables, and we do some calculations. So there's no additional space, okay? But this n times m term is a little slow. So in order to improve the efficiency of this code as well, what data structure can we use in this situation right? Where, you know, asking if something is in something else. That's not like the perfect opportunity for a set, right? Because a set, you're just trying to figure out, is this thing in this other thing, right? If you do a list, you have to look through the entire list. But if you do a set in amortized constant time, you can just grab that element out of the set, right? So what we can do instead is say B for Bob is a set version, or not B. Bob sizes is now a set of itself. So we took it from a list, we converted to a set. When we use a set, you get O of 1 amortized time questions when you ask, okay, Bob, instead of having to look through the whole list now when Alice gives him an element and he finds the corresponding element, now Bob takes that corresponding element and he just asks, is it in the set? And that happens in constant time, okay? So doing that should improve our runtime significantly. So before it was like 18, and now it's faster than 75. Right now, of course, there's high variance with this, right? But generally, of course, it's going to be faster because now we're using a set instead of a list, right? So what that basically does is now for all n of these, he asked this question, and instead of it being linear time, it's now constant, okay? So that means that this m goes away. 2n is just n, so it becomes just m. Now, the only downside of this is now that we've created this thing into a set, we had to take all the elements and create a set and then put it in it. So we've created a new set, which is the size of m. All right, guys. There's also another solution where you could get rid of this, and then you can make it n log m. So it's kind of like a two-sum problem. You know, you could just sort it, then you get an extra n log n term. So it gets a little more complicated, but you could make the space constant, or at least logarithmic. All right, guys. Hope you have a beautiful rest of your day. Bye-bye.